Hello, I'm Dane, and this is Dane Explains. You've probably heard of the word event horizon before. There's even a movie named after it. People often think it's the surface of a black hole. Even though a black hole sucks you in, you can never touch its event horizon. In fact, absolutely nothing can pass through it. Yet black holes across the universe devour many times the Earth's mass every second. Event horizons aren't confined to black holes either. Right now, there's even an event horizon sweeping across the universe, swallowing up everything as it goes, approaching the Earth from all directions. So, what is an event horizon? Let me explain. This is my second video in a short series of videos I'm doing. I released the first one last week. Luckily, understanding this one is not dependent on that one, so go ahead and watch it after this one. What I cover in that video will only seem tangentially related to this one, until you watch the last video in the series. An event horizon is what many people would say is the surface of a black hole. It's called an event horizon because the event that happens when you reach it is that you can never get out of the black hole. Nothing can, not even light. Hence why it's called a black hole. However, when you observe something fall into a black hole, you don't actually ever see the object enter. Basically, what you see is the object appears to move through time more slowly as it gets flatter, more redshifted and dimmer. And I did a video on what happens when you fall into a black hole, link in the description. Eventually, if you were still able to see it, in spite of the redshifting, the object would look completely two-dimensional and frozen in time, maybe one Planck length above the surface of the black hole. The moment it would be frozen in is the last moment before it crossed the event horizon. This idea is called the Holographic Principle. The main reason we can't see anything pass through a black hole is because of time dilation, an effect first proposed by the famous Einstein. And yes, it's proven, because if it wasn't compensated for by our GPS satellites, they'd be losing several miles of accuracy every day. Time dilation happens when something experiences acceleration, either due to gravity, like what all of us are feeling here on Earth, unless you're watching this from space anyway, or that feeling of being pressed into the seat when you push the accelerator on a car. It's a bit counterintuitive, but when you're feeling the pressure, you're accelerating. This makes sense when you're in a car and moving faster, but it also applies to gravity. So, the feeling of being pressed against the ground means you're being accelerated upwards by the solid ground. It's actually acceleration that produces an event horizon. This is why black holes create event horizons. Boiling things down, an event horizon forms when anything beyond a certain horizon needs to exceed the speed of light to reach you. Since nothing can go faster than light, it creates a black wall where not even light emitted by an object beyond it can reach you. An interesting effect that happens right at the event horizon is something called Hawking radiation, proposed by, you guessed it, Stephen Hawking. Simply put, it allows objects like black holes to radiate light. The easiest way to look at it is this. According to quantum physics, okay, I know, no sentence that says the easiest way to understand this should ever be followed by the sentence, according to quantum physics. Anyway, on a really tiny scale, particles can break the laws of thermodynamics and literally pop out of nowhere. However, they always have to appear in pairs, a particle and its antimatter counterpart. They can violate the rules because of the pair of particles recombine and disappear before they interact with anything. Now, what happens if this happens right on the edge of an event horizon, so that it separates the two particles? Well, never the two shall meet, and they become real particles. If this happens near a black hole, the particle that appeared on our side of the event horizon can escape the black hole and be detected. And in doing so, it steals a little bit of energy away from the black hole. Because the gravitational field changes more rapidly the smaller the black hole is. So that more intense gravity difference makes it so the black hole can separate the two particles more easily. So, the smaller the black holes are, the more Hawking radiation they release. This sapping of energy accelerates as the black hole gets smaller, due to the particles escaping, and eventually the black hole winks out in a flash of light. This is galaxy GN-Z11. It's currently the furthest known object in the universe, although the James Webb Telescope will hopefully make that a dated statement by this time next year. It's measured at 32 billion light-years away. The funny thing is, a light year is how long it takes light to travel in a year, and the universe is less than 14 billion years old. So how did the light from this galaxy reach us yet? Well, you've probably heard the universe is expanding. It's in fact expanding at an accelerating rate. So, objects far away from us aren't only moving away from us at some fixed speed, they're accelerating away from us. When the light was emitted from this galaxy, it was much closer to us, a little over 13 billion light-years away. It's also the reason why it's redshifted. Because of the accelerating expansion of the universe, the light emitted from this galaxy today can never reach us. What that means is it's already crossed an event horizon, and relative to that galaxy, we have crossed an event horizon as well. So technically speaking, depending on your perspective, we've already been swallowed up by an impassable event horizon. Galaxy GN-Z11 will slowly get redder and dimmer, just as if it was falling into a black hole. Eventually, it will be frozen in time at the moment it passed that event horizon, which, like I pointed out, already happened. But we can't see it yet due to the time dilation. Of course, we won't actually be able to see it because it will get to the point where any radiation released by the galaxy will be so redshifted that its wavelength will be longer than the observable universe, making it effectively invisible. So kind of like an inverted black hole. We have an event horizon slowly getting closer to the Earth as the universe's expansion accelerates. Eventually, everything beyond the galaxy itself will be beyond observation. However, due to the high gravity of the galaxy holding everything together, everything in the galaxy should remain observable effectively forever. Well, for as long as they emit light anyway. It's a lonely end. So, on galactic timescales, because things outside of our galaxy will be observable for much longer than we can physically visit them, if we want to have a chance to physically explore any amount of the universe beyond our galaxy, we'll have to get on that relatively soon. Another side note is, things will only happen this way if the universe's expansion is accelerating at a constant rate. Kind of like holding your car's gas pedal down only halfway and never changing it. If, however, it's accelerated at an accelerating rate, like pressing harder and harder on your gas pedal as time goes on, then the end will be much more exciting. That's something called the Big Rip. And the acceleration could be changing because different groups trying to determine the acceleration the universe is expanding at have got numbers that are different enough to be outside the margin of error. In the Big Rip, the event horizon formed by the expanding universe will overcome the power of gravity and start to swallow up stars in the galaxy, eventually closing in on the solar system, swallowing all the planets, the sun, and then even the Earth. The violence of the event would kill everyone on Earth before the event horizon reaches them. And even if you were floating in space wearing Iron Man's suit, the power of the negative energy would pop your body before the event horizon reaches you. If the force kept growing, it would eventually even tear apart black holes. The event horizon of the expanding universe would almost meet the event horizon of a black hole. But I think that's a discussion for another video. Thank you for watching. If you like this video, please press the like button, subscribe to my channel, and ding the bell to get notified when I post new videos. Also, please support me on Patreon, link in the description. The more people support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.